2017 has been a really quite big year for EE, with them regularly showcasing ever-increasing network performance, both in relatively controlled environments like Wembley Stadium, but also very much in the field. Alongside this, there have also been a number of quite futuristic type developments they have been undertaking as well. The first upgrade that I will talk about is the additional refarm of 1800 MHz spectrum from 2G operation to 4G. When EE first launched their 4G network all the way back in 2012, they did it refarming 1800 MHz spectrum from 2G to 4G, and the amount of 4G bandwidth has gradually increased over the years from 10 MHz paired as 4G at launch to then 20 MHz and now 30 MHz with the additional refarming that started happening this year. EE's main base layer 1800 MHz 4G carrier is 20 MHz paired with EARFCN of 1667. The new 10 MHz refarmed carrier bears the EARFCN of 1811 and it is 10 MHz paired. This does leave a fair amount of spectrum allocated as 2G for now, although of course in time additional spectrum of that 2G use will be refarmed to produce an even bigger second 1800 MHz 4G carrier in time. This screenshot also shows that both of the 1800 MHz carriers are operating in 44R, where the mast is using 4 transmit and 4 receive antennas to produce even higher performance, because not only does it substantially increase performance for devices that have 4 antennas in them themselves, the additional diversity on the mast side of things improves uplink and helps with cell edge user performance as well. So it is a major step beyond just improving peak speed as some people sort of visualize it to be. 44R isn't just found on 1800 MHz 4G, however. Some sites have it on 2600 MHz instead or as well. The combination of 44R on 1800 MHz and 2600 MHz, together with a technology that I'll talk about in the next slide, is how EE achieves their gigabit class 4G performance. The final piece in the puzzle to getting gigabit level 4G downlink performance is 256 QAM modulation, which yields around about a 1.3 times increase above the more typical 64 QAM downlink, which doesn't sound like much, but 1.3 times a relatively large number does lead to a fairly significantly positive delta in performance. EE has also been working to improve uplink performance as well, with 64 QAM uplink replacing the more conventional 16 QAM uplink, as well as uplink carrier aggregation, where 2 contiguous carriers on their network, so band 7 currently, to what I've seen, are aggregated together alongside 64 QAM uplink to yield a very significant uplift in uplink performance from a typical maximum before of around about 50 megabits per second to over 110 megabits per second upload, which is possible today. Through the use of a number of technologies that I've mentioned so far, namely significant spectrum combined with 44R and 256 QAM downlink, EE has achieved some superb performance both in Wembley Stadium as well as out in the urban environment as well. In Wembley Stadium they achieved 970 megabits per second with the Huawei Mate 10 Pro. Meanwhile in Cardiff City they achieved 430 megabits per second with the Sony XZ Premium, which is a Qualcomm Snapdragon X16 device. Download speeds well over 300 megabits per second are possible in many urban parts of the country thanks to EE's deployment of triple carrier aggregation between band 3 and then two band 7 carriers, which together can readily provide over 350 megabits per second of downlink performance, such as this test in Croydon where 378 megabit per second download speed was achieved. And actually this screenshot, as I showed earlier in the slides, also demonstrates uplink, carrier aggregation and 64 QAM uplink as well for over 110 megabit per second upload speeds. The additional refarming of 1800 MHz from 2G to 4G wasn't the only additional 4G bandwidth created this year. EE also started very recently to use spectrum that BT won in the 4G auction process for another 2600 MHz 4G carrier, this time bearing the EAR FCN of 3029 and having a bandwidth of 15 MHz paired. This means that EE can run up to 3 band 7 carriers with a total bandwidth of 50 MHz paired across them all, which is a colossal amount of band 7 2600 MHz spectrum. The ever-increasing demand on the network does not just have consequences for the permanent site grid in terms of spectrum and higher order MIMO and so on, it also affects how EE build their temporary sites in order to serve very high utilization but temporally restricted events. For example, Glastonbury Festival, where some fields which would ordinarily throughout the vast majority of the year have very, very little utilization suddenly get a huge density of users doing relatively intensive tasks like sending and receiving photos and videos on social media, and therefore specialised solution is required in order to provide a satisfactory network experience for users, which comes in the form of very high capacity temporary sites. These typically use multi-beam antennas with a lot of beams, so CCI antennas are very common in this sector, which for EE have 6 beams on them, and each of those beams will have a substantial set of spectrum as well, such as multiple band 7 2600 MHz carriers alongside 1800 MHz as well, and the full complement of all 4 3G carriers on 2100 MHz. The final 4G type technology that I'll talk about today is EE's addition of a higher quality voice codec using enhanced voice services over the IP multimedia system, or IMS, so that users with certain modern flagship handsets, like I think the iPhone 8, if both users are on EE and using VoLTE or Wi-Fi calling, then they'll be able to get a higher quality call than the standard HD voice that they would previously have used. How discernible it is, I can't tell because I've never used anything above HD voice, but the codec and data rate of it is a fair bit higher than the conventional HD voice, so presumably if you've got very good ears, the difference could be relatively large. In the final part of the video, I will speak about 5G new radio with regards to EE. At the Global Mobile Broadband Forum in November, EE and Huawei showcased decoupled uplink and downlink, where 5G new radio operating on the C-band provided the downlink from the site, and 1.8 GHz or 1800 MHz 4G provided the uplink from the device to the site. This is important because operating at very high frequencies, such as the C-band, If it's used for uplink, the range is very limited between the device and site due to the uplink power capabilities of a portable device, and therefore using a lower frequency for uplink means that you can get a good balance between having the very high capacity available from the bandwidths that are possible at these much higher frequencies like the C-band, while also having the good range from using a lower frequency like 1800 MHz, which is not so restricted in the uplink direction range-wise. From the image, it's also possible to discern that the 1800 MHz has 4 feeders between the antenna and the RIU, and therefore you'll get 4-way receive diversity on the 1800 MHz uplink. Meanwhile, the downlink panel is of a massive MIMO design, and therefore, very much as expected, it had massive MIMO on the downlink. This wasn't the only end-to-end 5G new radio with massive MIMO trial that EE has done with Huawei either. They also released a video showing their lab and a test that they did with Huawei, which achieved 2.8 gigabit per second end-to-end using a Huawei massive MIMO antenna, Huawei baseband, and then a variety of Huawei software virtualized onto kind of off-the-shelf HP servers as well, such as for the virtualized core. All in all then, EE has got up to really quite a lot in the year 2017, which will help them maintain their quality network experience against the oncoming tide of increasing network data consumption and general demand.